All right, now let's have a look at some more objects. So how about the distance between 2 points in space? Well, if I have a point P1 and a point P2, how do I find their distance? Well, the distance is given by the difference of their x component squared plus the difference in the y component squared plus the difference in the z components squared. I'd say, well, why is that the case? Why is this their formula? It looks like the distance formula between points in the plane with just an extra term added on, namely the difference in the z component squared. And the idea is that's exactly right. And that's how we can justify how to get the distance between 2 points. So if I let this be point P1, maybe I'll say that's P2 and this is P1. It really makes no difference, but I'll call the upper one P1 and the lower one P2. Then what I'm going to do is I'm going to draw a rectangular box that has these points at opposite ends. So our rectangular box is going to look something like this. And we'll keep drawing to give full perspective here. So there's our rectangular box. And now we want to think, how do I measure the distance across the diagonal of a rectangular box? Well, I can use an intermediate point. I'll use this one here, this point, let's call it Q. And I'll find the distance between P2 and that point Q. How am I going to do that? Well, remember this direction is the x direction, this direction is the y direction, and the up is the z direction. So what this distance here is that's the change in the y value. Q is really the projection of the point P1 down onto the plane that passes through P2. So P1 and Q, they have the same y value. So what is this difference? This is y1 minus y2. What is this distance? That is x1 minus x2. And so I have two sides, the two legs of this right triangle in the plane. And so I can find the length of that diagonal. The length of that diagonal is the square root of x1 minus x2 squared plus y1 minus y2 all squared. Now I'm really interested in the distance from point P2 to P1. And I can see that there is another right triangle here that I can use. I already know the length of the green side of it. The length of this side of that right triangle is the difference between Z1 and Z2. And so I can use the fact that the length of the hypotenuse of a right triangle is the square root of the sums of squares of the other two sides, or in other words, the Pythagorean theorem. So what we get is that length is going to be the square root of the square of the green side plus the square of the purple side. And that is exactly the square root of x1 minus x2 squared. Maybe I should have put this on a new line. Plus y1 minus y2 squared plus z1 minus z2 squared. And so that verifies our distance formula between 2 points. It was basically using the Pythagorean theorem twice. So now that we know how to compute the distance between 2 points, we can do that. What is the distance between P1 and P2? We denote this by writing P1, P2 side by side. That typically means the line segment from P1 to P2. That's just the notation for line segments in geometry. And then if we slap absolute value signs around it, that just means the length of the line segment. So that's where that notation is coming from. And then we just take the square root of the sums of the squares of the differences in their components. So we can go, I'll do the P2 components minus the P1 components. So it would be 2 minus 1 squared plus negative 3 minus 5 squared plus negative 3 minus 2 squared. Or in other words, it's the square root of 1 squared plus negative 8 squared, which is 64, plus negative 5 squared, which is 25. So that is 26 plus 64, which is root 90. Or in other words, root 9 times root 10, or 3 root 10 if we want to simplify it a little bit. And so there is the distance between those 2 points. Now that we have a distance function, the ability to compute distances between 2 points in three-dimensional space, this allows us to now talk about a fundamental object in three-dimensional space, namely the sphere. So let's assume we've been given a fixed point given by h, k, and l in space and a number little r. We want to find the equation of the sphere of radius little r with center big C. So how do we do that? The idea is we want to find the equation of the sphere. We've got this point C at the center and this radius r. How do we do that? Well, we have to think. What is the characteristic of points on the sphere? Points on the sphere consist of points with x, y, and z values, such that the distance from that point to the center point is r. So what is the distance from this to the center point? Well, the distance would be x minus the x-coordinate of the point at the center plus y minus the y-coordinate of the point at the center plus z minus the z-coordinate of the point at the center. Square rooted would have to equal r. So square root is equal to r. Or in other words, x minus h all squared plus y minus k all squared plus z minus l all squared is equal to r squared. And so there is the equation of a sphere in 3 dimensions. So very nice. It's an analog of the equation of a circle. Equation of a circle was basically just x minus h squared plus y minus k squared is equal to r squared. Now we've got the equation of a sphere, and it was just directly coming from the distance formula. So again, this is the equation of a sphere with, there's a few things we can read off of this, with center h, k, l, and radius r. So let's go ahead and look at an example where we've got an equation and we need to recognize that it actually describes a sphere. So show that this equation defines a sphere, and then we need to find its center and its radius. So in other words, we're thinking we've got the set of all points x, y, and z that satisfy this equation. What do the set of all such points look like? And it's going to consist of a sphere, which we're going to need to find the center and the radius. So how do we do this? Well, the way we're going to do this is we're going to group together the parts of the expression involving x. So we got 4y squared plus 16y plus a 4z squared is equal to 1. And now what we have to do is we have to complete the square for each of these components. So we'll factor out a 4 from this first part, and also a 4 from the second part. And now I'd like to write this as a perfect square, so it would be an x minus 1 all squared. And I have that 4 out front. So now I have to think, what did I actually add to this expression on the left-hand side? So I've got an x minus 1. When I square it, I get the x squared. I also get the negative 2x, but then I also added a 1 there as well, because the negative 1 times negative 1 is a 1. Not only did I just add a 1 there, I actually added a 4 times 1 because of that 4 out front. So I've just added a 4 to the left-hand side, so I better make sure I add a 4 to the right-hand side. And then we keep going, completing the square involving the y. That's a y plus 2 all squared. I've just added a 2 squared, or a 4 to this side, multiplied by the 4 out front. So I've just added a 16 to this side. So I'm going to need to add a 16 to the other side as well. And then we've got a plus 4z squared. So now I can divide through by 4. And I got that x minus 1 all squared plus y plus 2 all squared plus z squared is equal to 21 over 4. And that is the equation of a sphere. That matches the equation that we have up above. So we've recognized that, hey, that's an equation of a sphere with center. What is our center? It's 1, negative 2, and 0. Again, just compare with what we have up above. X minus h means h is the x component of the center. Y minus k means k is the y component, and so on. So we've got 1, negative 2, and 0, and radius. The square root of 21 over 4, or in other words, root 21 over 2 is our radius. Okay, so that's it for this section. The idea was to introduce three-dimensional coordinate system and to realize that once we have the coordinate system introduced, we can talk about equations which describe certain surfaces. So we were given equations, we were able to figure out what the surface is that represents them, and we also got to a little bit more advanced surface, such as the sphere. And now in the next section, we're going to introduce one more set of tools that we're going to need to work in 3 dimensions, and that is vectors. So we're going to introduce vectors and then a little bit of vector geometry, dot products, cross products, and the like. And then once we've got those foundations behind us, then we can get into calculus. All right, thanks for watching, and we'll see you in the next lecture.